Hi, my name is Katie Schweitzer, and I am a first-year master's student at the University of Maine in the Structural Engineering and Mechanics program, and I'm advised by Dr. Roberto Lopez-Nito. My thesis work encompasses the recyclability of large-scale 3D printed formwork, and so a little background into why we are doing the work we are doing is precast concrete is widely used in transportation infrastructure. However, traditional formwork is expensive, labor intensive, and general in geometry. So large scale 3D printed formwork can offer more economic and environmentally friendly alternative to traditional formwork while lifting geometric limitations and lessening cost due to the fact that 3D printing is a automated manufacturing process. And this work is meant to evaluate the economic viability and environmental impact of the recycling process of large-scale extrusion-based 3D printed thermoplastic concrete formwork. So the materials that I will be evaluating and will be working with and have been working with are carbon fiber, acrylonitrile butadiene styrene, and wood flour amorphous PLA, polylactic acid. The wood flour PLA is completely bio-based, while the carbon fiber ABS is completely synthetic. And both of these materials have a 20% reinforcement by weight. So to evaluate the viability of recycling, I needed to establish a baseline material properties, and the baseline was determined using the first set of 3D printed formwork, and a total of 2 sets of formwork were manufactured at the Advanced Structural Composites Center at the University of Maine using the Ingersoll master print. And a set of forms consists of 5 wood flour APLA forms and 5 carbon fiber ABS forms. So the baseline properties that I established included glass transition temperature, fiber reinforcement length, material impurities, tensile modulus, and tensile strength. Differential scanning calorimetry was used to determine glass transition temperature, while thermogravimetric analysis was used to determine the material impurities after casting the concrete in the forms and washing the forms. So this was also able to tell us the effectiveness of our washing methods. And fiber length was determined with a matrix dissolution and microscopy using a scanning electron microscope and ImageJ software. And a modified ASTM standard D3039 with digital image correlation was used to determine the baseline tensile modulus and tensile strength of the material. So following the establishment of the baseline, it will be possible to see any deterioration in material properties with subsequent recycling cycles. And my project will complete a total of 6 recycling cycles. And a cycle consists of printing the formwork, conducting the thermomechanical tests to obtain the material properties, casting concrete, washing the forms, grinding the material, and pelletizing the material into new feedstock to print with. And looking ahead, now that I have established a baseline of material properties, the forms will be shipped to our project collaborators, Oak Ridge National Labs. And at Oak Ridge National Lab, the forms will be ground and pelletized into new feedstock material. And with this new feedstock material, it will be possible to print our first recycled set of forms. And then we will be able to determine any deterioration in material properties after the first print. Thank you.